Today we will be calculating net force. Our goal is to connect and extend previous understanding of the forces to find the net force. Today we're going to use the force. So let's get started. First, let's review some important vocabulary. So we remember that a force is a push or a pull on an object. And then in the last video we went over that force is actually a lot more than that, because even when an object isn't moving, it is being, there are many forces being acted upon it, such as gravity and the force of the earth pushing back on the objects. So it is important to know that it's more than that, but our basic definition to review is a force is a push or a pull. An unbalanced force causes change in motion or direction. And a balanced force has no motion. It has a net force of 0, usually. Or it's in constant motion at the same velocity. Net force is the combination of all the forces acting upon an object. And we label net force in newtons. So let's look at some examples on how to calculate net force. How do we calculate net force? Well, when two or more forces are acting in the same object, in the same direction, you add the forces. For example, if I have one mover moving a giant refrigerator 25, and again, it's always newtons, to the right, and the other mover helping out also moving 25 newtons. Let's say it's 20 because moving backwards sometimes it's a little less. You would add the two forces. Again, they are in the same direction. So it would be 25 newtons plus 20 newtons, equals 45 newtons to the right. And I'm just going to point the arrow to the right. So when two or more forces are acting in the same object in the same direction, you add the forces. And again, they're both positive. They're both going in the same direction. So it would be to the right in this case. The arrows are what's always going to help you. And the first thing we always are going to do is draw a free body diagram, which is usually a box with a dot in the middle. And then you have to decide which direction is positive and which direction is negative. That direction can be right, left, up, or down for our purposes. Let's look at another scenario. When two or more forces are acting in the same object in opposite directions, you subtract the forces. Again, you also have to decide which side is positive and which side is negative. So if I was going to draw a free body diagram, I would have a box with a dot in the middle, and I would have an arrow pointing in opposite directions. And in this case, let's say that the smaller dog is 10 newtons, and then the larger dog is 12 newtons pulling on this. So in a game of tug of war, you would be able to predict the winner. So your net force is unbalanced. So we have 12 newtons to the left and 10 newtons to the right. You would subtract the forces and you would have an unbalanced force to the left of 2 newtons. So 2 newtons to the left of the object in this case with these numbers. So you're going to subtract the forces if they are in opposite directions. And you would again decide which side is positive and negative. And it really doesn't matter which side you decide is positive or negative, because if you subtract two negatives, for example, you would add the opposite, it does balance out mathematics-wise. But it is important to know if the force is in favor of up or down, right or left, and the direction. Another important thing to note is that when two forces are balanced, they do not move, and the net force is 0. So our net force is 0 if they cancel each other out. So if I have two people with the same mass and the same amount of strength playing tug-of-war in opposite directions, let's say it was 25 newtons left and 25 newtons right, they would balance out. So I would have 25 newtons minus 25 newtons, because these are opposite directions, so I'm subtracting, and that would give me a net force of 0 newtons. Let's look at some more examples, and this time we're going to draw some free body diagrams. There's an accompanying foldable that looks like this that should help you with these activities. So we have our free body diagram, and we're going to look at some different examples of net force calculations. So let's look at one example. If we look at an example with a free body diagram, and of course I made my box a little more colorful for video purposes, but you would again draw a box with a dot in the middle, and if you have a force of 25 newtons to the right and another force of 25 newtons to the right, you would have them going in the same direction, so it would be 25 newtons plus 25 newtons to the right. If they're both to the right, you add them and you would get a force of 50 newtons, because 25 plus 25 is 50. Go ahead and pause the video at any time to make sure that you have careful notes. What if we have it in opposite directions? Of course, if it's the same force in opposite directions, they'll balance each other out, but we can see that because these numbers are not the same, they are not balanced. And again, you can think of which side is positive and negative, but in this case, subtracting the larger from the and the smaller is usually easier, and just knowing which one is bigger, kind of like how you subtract positive or add positive and negative numbers. If your larger number is positive, your answer will be positive, and if your larger number is negative, your answer will be negative. So if we look at this example, in this case we have right versus left. The larger number is 25. 25 is greater than 18. Therefore, our larger number is going to be where our direction is pointing, which in this case is to the left. And again, you can use positive and negative integers in dealing with newtons as well. But in this case, since we're talking about direction, we want to say that the answer is going to be favorable to the left in this case. So we have 25 newtons minus 18 newtons, which would give us 7 newtons. And again, 7 newtons going to the left is the stronger force. So if we had two people pushing on an object, the object would move to the left, not to the right, because the stronger force is being applied in the direction of the left, because they're both pushing. These are, of course, pushing forces onto this object. Looking at another example, now we have a force going north and south, or up and down, however you want to describe the direction. But if we have a force going on top and then again below in the same direction, because keep in mind these arrows, no matter where I put them, are pointing in the same direction. we have same direction, we add. So we have 14 newtons down plus 36 newtons down, or we can call it south, gives us a total force of 50 newtons down. And direction is really a matter of perspective, but I like to give you different examples, not just left or right, but up and down as well. So this would be 50 newtons in a downward direction, pushing down, or south if you wanted to call it north, east, south, or west. Let's look at yet another example. We again have arrows pointing in opposite directions. One's pointing up, one's pointing down. And we can again look and see which number is greater, 25 or 8. Well, 25 is greater than 8, so I know my answer is going to be favorable up. So it'll be however many newtons up. So if I have one of each, one arrow of each direction, I'm going to subtract because we're applying force in opposite directions, so we subtract them. So we have 25 newtons minus 8 newtons, and then of course one's up, one's down. That gives us 17 newtons, and it's going to be favorable up. So 20 newtons up is our answer. Or sorry, not 20, 17 newtons up. So again, it can be left, right, up and down. Let's look at one final example. Again, we have a force in opposite directions. One is pointing to the right, one is pointing to the left. And comparing our numbers, 65 is greater than 25, so I know my answer is going to be with a force to the left, because that's the direction of this arrow. And so we have to subtract, because we again have opposite forces and we need to subtract them because they're in opposite directions. So 65 newtons to the left minus 25 newtons to the right, again because they're opposite, I'm subtracting, gives us 40 newtons, again to the left. Sorry about my arrows, because there's greater force applied in the direction of the left. So if somebody was trying to stop a mover, for example, like if this was a large item like a refrigerator in some of the examples, or a television set, and there was someone trying to stop you from moving it, but maybe it was something with a very little force, it would still be able to move to the left, but just not as fast as it could have had there been no counter movement or pressure in the other direction. So often this is a case of friction. It's a whole lot easier to move a heavy object when you have a smooth, frictionless surface versus if it's a really jagged or rocky surface. It can be a lot harder to move something across that surface. One question I get after some of these examples can be, well, things aren't always up and down, left or right. Is there another way to calculate direction if it's going in a circle, for example? And the answer is yes. That's when we get into vectors, which we will get into in later videos in a little bit more complicated math. But for now, we are going to be dealing with more basic up and down, left and right motions with simple addition and subtraction. So looking at your notes, the top will look like this if you use the template that I gave you. underneath, you'll have written the problems. And again, those arrows, having the direction with them is important. So don't just write 50 newtons. Write 50 newtons to the right, to the left, up or down. Make sure you're putting the direction. And I even added color to it to make sure I added it and really highlighted it in my notes. So in today's lesson, we calculated net force. We used basic addition and subtraction to find the net force applied to the objects, the total net force in the direction. So I hope that you understand that calculating net force helps you better understand how things can move and better understand Newton's laws of motion. Thank you again for watching, and as always, have a great day. Bye!